Hello everyone. As you know, yesterday JEE Advanced 2025 was conducted. So from today, I am starting to record one by one solution. So each problem, I'll discuss the solution step by step. So let's start with the question number one. So this question says that the center of the disk of radius r and mass m is attached to a spring of spring constant k inside a ring of radius capital R greater than small r. So there is a disk which is having mass m. It is also having radius of small r, and it is oscillating inside the ring. The other end of the spring is attached to the periphery of the ring. Both the ring and the disk are in the same vertical plane. The disk can only roll along the inside of the periphery of the ring without slipping. The spring can only be stretched or compressed along the periphery of the ring. Following Hooke's law, in equilibrium, the disk is at the bottom of the ring. Assuming the small displacement of the disk, the time period of oscillation of the center of mass of the disk is written as 2 pi by omega. The expression of omega we have to find out. So see, we'll first draw one very general condition. Let's say this is a ring surface on which the disk is rolling and oscillating, of course. Let's say at any instant, the angular position with respect to the ring center is phi. And this phi is a varying quantity because it is oscillating. So phi is reducing and increasing, all these things are happening. At the same time, this disk, which is having mass m and radius r, this is also rolling on this surface, ring surface. Let's say that any instant, the angular velocity of the disk is omega. Now, what is the condition for pure rolling? The condition for pure rolling is the center of the disk linear velocity should be equal to r of omega because the point of contact should not have any velocity. That is the condition. So V should be equal to r into omega, where r is the radius of the disk, omega is at any instant, let's say that is the angular velocity of the disk, and V is the linear velocity of the center of the disk. Now, what is the linear velocity of the center of the disk? See, this phi is changing. So there is some phi dot. So from the center of the ring to the center of the disk, the distance is capital R minus of small r. So the distance, this distance is going to be capital R minus small r. So the V, or the linear velocity of the center of the disk, is going to be capital R minus small r into phi dot. That is actually r of omega. So omega relation with phi dot we'll be able to find out. So what is the relation? Omega is capital R by r minus 1 into phi dot. So omega is also a varying quantity. So omega dot also we can find out. R by r minus 1 is constant. So omega dot is phi double dot. Basic thing we have done. Now, we know that SHM, as there is no dissipative force, total energy of the disk will be conserved. Or we'll write total energy of the disk is constant. So kinetic energy will be converted to potential energy, and potential energy will be converted to the kinetic energy, and this will happen for infinite time. So total energy of the disk is constant. So two components of total energy is, one is kinetic energy, another is potential energy. So there will be two components of kinetic energy because the disk is rotating as well as having some linear motion. So the kinetic energy will have two components, that is translational kinetic energy, TKE, plus rotational kinetic energy. Potential energy also have two components. One is due to the gravitational potential energy because as the disk is rotating, it is having or covering some vertical distance. If G is acting downward, it is covering some vertical distance also. So there will be some component of gravitational potential energy. And at the same time, as the spring is going to be stretched and compressed periodically, it is going to have spring potential energy, and total of that should be constant. So translational kinetic energy is at any instant, if the velocity is v, then half of mv square I can write. At the same instant, if the angular velocity is omega, I can write half of I of omega square, rotational kinetic energy. Now we'll come to the gravitational potential energy. Now we'll again draw one diagram. This is the ring surface on which the disk is rolling and covering the vertical distance. Let's say at any instant, again I'm drawing the angular displacement with respect to the ring center, it is phi. So this distance, now we'll consider only center to center distance because that is where the spring is attached. So while the disk was at the bottom of the ring, that time this was the position of the ring. Right now, the disk. Right now, the position of the disk is changed. So what is going to be the vertical displacement of the center of the disk? This much only. That is capital R minus this is capital R minus R. And after it's displaced by phi angle, this distance is going to be capital R minus R of cos phi. So the vertical distance, that is capital R minus R minus of capital R minus R into cos of phi. So it is going to be capital R minus R of 1 minus cos phi. So that is the vertical distance for phi angular displacement with respect to the ring center. So we can write the gravitational potential energy is mg delta H, mg capital R minus R 1 minus cos phi. Now we'll come to the spring potential energy, that is half of k of spring extension or compression square. So see, the spring is attached to the center of the disk. So the extension of the spring is going to be this much only. This is the extension of the spring delta x. What is that? As the spring is attached to the center of the disk, this distance from the center of the ring to the center of the disk is capital R minus small r. I'll change the color. So this is capital R minus small r. So this distance is going to be capital R minus small r into phi, r of theta. So here r is r minus small r. So it is r minus small r into phi. So the spring potential energy is half of k of delta x square. So delta x we have found out, that is into phi square, that is equal to constant. Now our basic energy equation is formed. Now we can do the differentiation with respect to time. So half mv square plus half of I omega square, half of mv square plus half of I omega square plus mg capital R minus small r 1 minus cos phi plus half of k r minus r square of phi square. Entire thing should be 0 because total energy is constant. Now I can write half of mr square, and b we can write, that is r of omega, because we have established the relation between omega and phi. So I'm just expressing everything on omega so that we can substitute the value of omega in terms of phi or phi dot whatever. That's it will be. So half of m of r square by 2 omega square plus same thing will be there, 0 ddt of that. Now half of m r square plus 1/4 of m r square, that is going to be 3/4 of m r square omega square d dt plus mg r minus small r 1 minus cos phi plus half of k r minus r square phi square, that is 0. Now we can directly differentiate. Now we'll come to the differentiation part. So 3/4 m r square is constant, omega is varying. That is, differentiation is going to be 2 omega of d omega dt, and d omega dt is alpha. So we can write alpha plus mg into r minus r, all is constant, all are constant. So 1 is also constant. So the differentiation of cos phi is going to be minus cos phi sin phi into phi dot plus phi square. Other terms are constant terms. So phi square differentiation is 2 phi dot. 2 will cancel out. So ultimately phi dot into k of r minus r square, that is 0. Now here 2 will cancel out. So we are getting 3/2 m r square omega alpha plus mg of capital R minus small r sin phi. Sin phi here I can write as phi because phi is a very small angular displacement. So I can directly write instead of sin phi, that is phi. For SHM, we can write sin phi equal to phi. So phi dot plus again phi dot k r minus r square equal to 0. Now, this equation we got. In this equation, the variables are omega, alpha, phi dot. But we have already established the relation of omega and alpha. This is alpha. So we'll just put that so that all other variables is converted to one single variable, that is phi, because phi is the displacement, angular displacement. So 3/2 m of r square omega will put, that is phi dot of r by r minus 1. Alpha will put phi double dot r by r minus 1 plus other terms will be same, r minus r phi dot plus k of r minus r square phi dot equal to 0. See, we are able to cancel out phi dot. We use another color. So the first term is becoming 3/2 m r minus r square, because this r square and the denominator r square will cancel out. We'll get ultimately r minus r square into phi double dot plus we are getting mg r minus r plus k of r minus r square. Entire thing is multiplied with phi, that is 0. Now we're getting phi double dot plus mg of capital R minus small r plus k r minus r square by 3/2 of m r minus r square phi equal to 0. Is it looking very similar to the SHM equation? These are SHM equation, standard SHM equation. You see, we are getting omega square is this term, entire term is omega square. So we got the value of omega square to be that one, that is mg. We'll just divide the entire thing by the denominator. So it is going to be, we'll just write here only, we'll convert and write, that is 2g by 3 of r minus r, plus if we divide that term is going to be 2 by 3 a by m. So we are getting 2 by 3. If we take common, I'm getting g by r minus r plus k by m, that is the omega square. So we are able to find out what is the expression of omega, that is 2/3 of g by r minus r plus k by m. So see which answer is matching. The answer is option number A. That is the correct answer. So next question, paper 1, question number 2. In a scattering experiment, a particle of mass 2m collides with another particle of mass m, which is initially at rest. Assuming the collision to be perfectly elastic, the maximum angular deviation theta of the heavier particle, as shown in the figure in radians, you have to find out. Okay, so as after this collision, both masses are going at an angle, so it must be oblique collision. It is not head-on collision, because in the case of head-on collision, both the mass will go in a straight line only, in that impact line only. So this is oblique collision. So let us assume, we have to assume many things here. Let us assume that initial velocity of the mass 2m, that is v, initial velocity of mass small m, that is 0, it is told it is at rest. So after the collision, it is the 2m mass is going at an angle theta. Let's say it is going with velocity of v1, and mass small m, angle is not mentioned. We have to assume the angle. Let's say phi is the angle, and velocity also have to assume v2 along this line. So we'll just do the momentum conservation first. Momentum conservation. Along x. So initial momentum 2 into m into v is going to be equal to 2 into m into v1 of cos theta plus m into v2 into cos phi. You can simplify it. 2v I can write 2v1 cos theta plus v2 cos phi. Equation number 1. See how many unknowns we're having. We're having phi unknown. We are having v2 unknown. We are having v1 also unknown. So 3 unknowns we are having, keeping in mind that initial velocity is something constant. Those are the unknown quantities. So we have to at least find out 3 equations so that we can express other variables or other unknowns in terms of one unknown only. So of course, another momentum conservation will be along y-axis, along y. Along y-axis, initial momentum was 0. 0 is ultimately 2 of m v1 sine theta minus m v2 sine phi. Again, we can simplify it and we can write 2v1 2v1 sine theta is equal to v2 of sine of phi. This is our equation number 2. Then another equation that can come, that is, of course, the kinetic energy equation. Initial kinetic energy will be equal to final kinetic energy because it's perfectly elastic collision. All conditions are given. So half of 2m into v square, that is the initial kinetic energy, and final kinetic energy is going to be half of m of v1 square plus, sorry, half of 2m into v1 square plus half of m into v2 square. That is our third equation. So we can also simplify it. So we can write v square is going to be v1 square plus v2 square by 2. So we can directly write plus v2 square. That is our third equation. See what kind of elimination we can do. So from equation number 1 and equation number 2, we can eliminate phi here. So we can express v2 cos phi in terms of v and v1. So we are getting 2v minus 2v1 cos of theta. From equation number 2, we already know that is v2 of sine phi. That is going to be 2v1 sine theta. So from these two equations, v2 cos phi and v2 sine phi, we can eliminate phi by squaring and adding them. So ultimately, I'm getting v2 square. If I add this, square this and add this, I'll get v2 square is 2v minus 2v1 cos theta square plus 2v1 sine theta square. So I'll get 4v square minus 8v v1 cos theta plus 4v1 square cos square theta plus 4v1 square sine square theta. Ultimately, it will give 4v1 square, that is equal to v2 square. Now see, in our third equation, what we got? Third equation, we got 2v square equal to 2v1 square plus v2 square. So v2 square, if you want to eliminate, because that all we have assumed, phi and v2 we have assumed. So v2 I can eliminate in terms of v and v1 and theta, of course. So we'll just do that. Plus 4 v2 v square minus 8v v1 cos theta plus 4 v1 square. So finally, my motto is to get some term of theta in terms of other v or v1, some variable term. So v if we constant, so v1 will be the variable, and we can, so that we can differentiate with respect to that, and we can make that 0 in order to make the maximum, find out the maximum angle. That's our goal. So 8v v1 cos theta, I can write 6, not 6, 2v square plus 6v1 square. I think that is right. So that means 4v v1 cos theta is v square plus 3v1 square. So see, I can write cos theta as v square plus 3v1 square by 4v v1. Now see, if initial velocity v is constant, so I have to find out the maximum value of theta. So I can differentiate directly with respect to v1 because v1 here is the variable. So if I differentiate, it is going to be minus of sine theta into d theta of dv1 is going to be the first term, of course. Then write the inside terms is v by 4v1 plus 3v1 by 4v. So dv1 is going to be minus v by 4v1 square plus 3 by 4v. So see, for the maximum value of theta, the d theta dv will be 0. That should be 0. So if I make it 0, then this term should be 0. Ultimately, I'll get v1. What is the value of v1? So v by 4v1 square is going to be 3 by 4v. So v1, I am getting, that is, it is v by root 3. Yes, getting v by root 3, v1 value. So for this value of v1, that is v by root 3, we'll get the maximum value of theta. We can directly put that in our cos theta, whatever we have got. Cos theta is v square plus 3v1 square by 4v v1. Can directly put the value of v1 for the maximum value of theta. So if we put that, we'll get 3 of v square by 3 by 4v of v by root 3. So ultimately I'm getting 2v square by 4 by root 3v. So it is becoming v square root 3 by 2 I am getting ultimately. So the value of theta is pi by 6. That is our answer. So answer is option number D is the correct answer.